Okay, so we're going to cover how to figure out what kind of pedigree you're looking at today, as well as how to figure out the genotypes found within the pedigree. Okay, so a pedigree is going to give us genetic information on a family, okay, and it will follow a particular trait as it goes through that family. And as you look at the information given in the pedigree, you can determine what kind of pedigree it is, what kind of trait that is that's being passed through the family. So some information that you would need to be able to analyze a pedigree would be the fact that squares are males, okay, and circles are females. If something is shaded, then they have the trait. Okay. If they are unshaded, then they are normal or do not have the trait. And by having the trait, we're talking about expressing the trait. So they could be a carrier and they would still look normal, so they would be unshaded. So by having the trait, their phenotype shows that they have this particular, they're expressing this particular trait. Same with females. If it's a shaded circle, it's a female that is expressing that particular trait. If they are married, you'll see a line that connects the two of them right in the middle there. If they are divorced, that line will be marked out. Okay. Siblings would come from the marriage, as a general rule, they come from the marriage line, okay, and they will be connected by a line on the top here, not connecting them through the middle of the two shapes. And then if someone has died, okay, they are not erased from the pedigree, they are just crossed off. So our three different types of pedigrees are autosomal dominant, autosomal recessive, and sex-linked recessive. And so what you're looking at here, and on your handout, remember your handout is your notes. So you need to go through them, you need to be marking them up, highlighting, writing things on them, so that you can put that into your notebook. So the first kind of pedigree is an autosomal dominant pedigree. And so with an autosomal dominant pedigree, you are looking at a trait that is going to be dominant. And so if it's a dominant trait, that means it's carried on the dominant allele. And so it is going to, as a general rule, will show up more often. Somebody that's heterozygous, this genotype here would express the trait. This genotype here would express the trait. The only people that are not showing the trait have to be homozygous recessive with an autosomal dominant trait. So this trait will appear in every single generation. So every line of your pedigree is going to have at least one person in it that is going to be shaded in. And every person that is affected is going to have a parent that is affected. Every person with the trait has at least one parent affected with the trait. In your autosomal recessive pedigree, you're looking at a trait that is a recessive trait. So you've got your three different genotypes, and in this case, the homozygous recessive is the only one that has the trait. Okay? Whereas in the autosomal dominant, that'd be the only person that did not have the trait. So if it's an autosomal recessive pedigree, you can have people that are affected with the trait. However, their parents are not affected. You could have two heterozygous parents, which gives the possibility of having someone with a trait that is affected. So you can have people that are unshaded, they're normal, but they have offspring that are shaded, that have the trait. And with a sex-linked recessive pedigree, it's going to be most common in males, so you'll have significantly more squares shaded than you will have circles. So more common in males, and a female can have the trait only if her father has the trait. Okay? Remember, females are XX, males are XY. So if you have a daughter, then the father had to pass on the X chromosome. So, and remember, the only way females can have a recessive trait is their X little d, which means the dad had to have been able to pass on at least one X little d. So dad had to be affected because, remember, males cannot be carriers for sex-linked recessive traits. So those are your three pedigrees, and that's the rules you would determine to figure out which one is which. So using those rules, let's look at this particular pedigree and see if we can determine which kind it is. So if we look at it, each one of these rows, okay, each row here, that's a generation. So in this particular pedigree, every generation has someone that has the disease, expresses the trait, and every person that has the trait, okay, if you follow it back up, they have at least one parent that is affected with the trait. So this pedigree would be an example of our autosomal dominant. So when we're determining genotypes for an autosomal dominant pedigree, remember we have 3 possible genotypes: big H, big H, big H, little h, little h, little h. So in this particular case, okay, if it's an autosomal dominant trait, then that means people that are big H, and big H, little h, they express or show the trait. So that tells us every single person that is shaded has at least one big H. We know that much. Okay, so they all have at least one big H in their genotype. We also know that unshaded people do not have the disease or do not expressing the particular trait. So in this particular kind of pedigree, the only people that do not express the trait, they are people with the genotype little h, little h. So we have to have all the unshaded people we know have to have the genotype little h, little h. Okay, so now the quote-unquote tricky part would be to figure out whether they are heterozygous or they are unknown. When you are writing pedigrees, genotypes on pedigrees, you will never, ever, 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 and some more never, ever write homozygous dominant. You will write that they are heterozygous or that they are unknown. That if you don't know their parents, you may not know the information about their parents, and they could always have another child, and that child could reveal information that shows that they are heterozygous or not. So you always put unknown. So when we're determining that, we're going to use people's parents and offspring to decide whether they are heterozygous or they are unknown. So if we look at this first individual here, this male right here, okay, this male has children, and he has children that are homozygous recessive, which means they had to have gotten a little h from mom as well as a little h from dad, which means this dad has to be heterozygous. He has to have a little h to pass on to the offspring. Now if we go look at this individual here, this individual, he doesn't have any children, so we can't use that. But if we go backwards and look at the parents, we see that his mother is little h, which means the mom can only pass on a little h. So he has to be heterozygous. His sister over here on the end, individual number 4 here, she has to be heterozygous for the same reason. Her mother only has a little h to pass on, as well as she has a daughter, okay, that is little h. So she has to have a little h to be able to pass that one on. Okay, let's go look at her children. In generation number 3, so in the 3rd row down, individual number 1 and individual number 3, their brother and sister, okay, they are both going to be heterozygous. And they're going to be heterozygous based on their father. If you trace it back up to their father, he is little h, so they had to receive a little h from him. Now when you go over here to her husband, generation number 3, individual number 4. Okay? You don't have any information on his parents, and they have 3 children, but none of those children are homozygous recessive. So that does not tell you that he is homozygous dominant. That tells you that he is unknown. What if they had a 4th child, and that 4th child did not express the trait? Then he would be heterozygous. But you don't know that. Okay? So he becomes unknown. Same with all of their children. Okay? With all of their children, you have no idea. Since you don't know what dad was, they don't have any children, okay? You cannot determine that they are heterozygous, so you can only determine that they are unknown. Remember, you will never write homozygous dominant genotypes on your pedigree. Okay? So on your handout, up at the top here, they have these rules, okay, for finding these. I think it's pretty logical, though, for most of y'all, but again, you can refer to those rules. There's some questions down here at the bottom, okay, which individuals are female. When you write individuals, that's based on the generation as well as the individual number. For instance, in generation 4, in this bottom row down here, generation 4, individuals 2, generation 4, individual number 3. They are both female. So that's how you would write individuals. Right? Same with individuals that are male. For example, generation 4, individual number 1 is a male. And you would list those for every single individual because that's what the question asks. We already did number 3. We've already talked about number 4. Okay? If you look at number 5, 6, 7, these are relationship questions. So we'll do 1 or 2 of these and then we won't do them on the other pedigrees. You'll do them yourself. Okay? What is the relationship between individual 3, 4 and 3, 1? So if we come up here, we're looking at generation 3, individual 4, and generation 3, individual number 1. The relationship between those two, they're both males. Their relationship would be that they are brothers-in-law. Okay, if we did one more, individual 4, 2, and individual 3, 1. Okay, so individual 4, 2, that's this person here, and individual 3, 1, that's that guy over there. Okay, so their relationship is the first individual was individual 4, 2, so that is the niece and uncle. Okay, and then so any other relationship questions you guys will do on your own. I think you can handle that by yourself. There is a probability question here. So we would solve this probability question by using the pedigree to develop a Punnett square. The probability of individuals 2, 4 and individuals 2, 5 having another child with a disorder. Sorry about that, I just wrote this big blue streak there. So 2, 4 and 2, 5. So we are up here with these two, okay, a heterozygous and a homozygous recessive. So our genotypes are this. So I would just draw my Punnett square, okay, and that's how I would solve for that particular question. So my probability of them having another child with the disorder is 2 out of 4, 1/2. If it asked percentage, it would be 50%. Okay, so let's look at this next pedigree here. So in this next pedigree, you do have somebody in each generation that has the disorder. You have somebody in each generation that has it. However, you have individuals who have the disorder, but their parents do not. So that makes this one, instead of being an autosomal dominant, even though someone in every generation has the disorder, you have people who they have it and their parents don't. That makes this an autosomal recessive pedigree as opposed to an autosomal dominant pedigree. So same for this. We're going to look for genotypes with this. So again, we have big T unknown, big T, or little t. Those are our 3 options. So since this is an autosomal recessive pedigree, we know everyone that has the disorder has to be homozygous recessive because it's a recessive trait now. So now all our shaded people are homozygous recessive. So that's easy. So that leaves all our unshaded people to be one of these two. They do not have the disorder, so that means they have to have at least one dominant because they're not expressing the disorder. And then we would need to go back and determine if they were heterozygous or unknown. And we do that very similar to how we did it in the autosomal dominant pedigree. For instance, this female up here, generation number 1, individual number 1. She has a son, okay? She has a son here who has the disorder, which means she had to have a little t to pass on to that son. Okay? Then if you go to your next generation, generation number 2, individual number 1. He is actually an unknown because you don't know anything about his parents. You know about her parents. So his wife is heterozygous because his wife's father is little t, but you don't know anything about his parents and you don't know about their child. That also then makes their child unknown. Neither one of the child's parents have the disorder,